In this video, I'm just going to do a quick review of time series forecasting. Time series forecasting essentially deals with the case where we have data that is chronologically ordered. So for example, if we're looking at sales data, the data can be ordered monthly, quarterly. We could look at, say for example, the size of queues in a sort of a restaurant, for example, and we could look at the data hourly, the first hour, second hour, third hour, and so forth. So as long as the data can be chronologically ordered, then we are dealing with time series data. All right. And so if you were to plot it, you could always plot the data where on your x-axis there would be time, and on the y-axis whatever that we're observing. So if we're looking at sales, we could have data that looks like something like that, and so that would be an example of time series data. So when we want to forecast, what are some models that we can use? I mentioned a moving average is very popular. We also have a model called a naive model. Then we have exponential smoothing. We also have trend models. Right? So these are all examples. And then we also have exponential smoothing with trend too. Exponential smoothing, I'm just shortening this, with trend. And the reason for that is because the exponential smoothing model has a tendency to lag behind when trend is present. Okay. Now we have some non-time series models which we refer to as associative models. And associative models means that we have y as a function of some variable x, or it could be x1, x2, xn, or xm, which is basically, there are a number of independent variables of which y happens to be a function of all of those. All right. So if we're looking at your basic naive model, with the naive model, the way it works is that we say that the near future will look like the not too distant past. So tomorrow will look like today, the day after tomorrow will look like, tomorrow, and so forth. Or if we want some to represent seasons, we could say this February will look like last February. March coming will look like last March, and so therefore in that case we are considering seasonality. What if we wanted to consider sort of a trend effect? Well, we could say, well, what was the increase from January to February, or decrease? It could be an increase or a decrease. If that's the case, then we would, let's say if that increase was, say, 10%, we saw somehow 10% growth, we will assume between February and March that we'll see some 10% growth as well. And that's an example of applying a naive approach to trend. So there's not a lot of calculations that we do in this case. When we get to moving averages now, we could talk about a simple moving average or weighted moving average. So a moving average forecast will basically means that we take a number of periods and we average them. So a formula typically would look something like this. So moving average, the forecast for a period T would be the sum of AT minus L, which is the actual demand or the actual values, where L is equal to 1 to however many periods we want in our moving average. Let's say we want m periods. So if m is just 2, we would take t minus 1, which is the previous period, and then t minus 2. And then we would average that by dividing by the number of periods we want in the moving average. And that would be our moving average forecast. Now what if we had weights to this? If we wanted to make it a weighted moving average, we could simply add a weight in here, WL. And WL would be such that the sum of WL, L equal to 1 to m, that means the weights would just add up to 1. Alright? So in your simple weighted moving average, essentially the weight is 1 over m. So if you had a 2-period moving average, then you're weighting each value equally, which means that it's 0.5, 0.5. 1 over 2 is 0.5. If you have 3 of them, you're weighting each of them 1/3. Right? When you divide by 3, you're weighting each of them 1/3. That's in a simple moving average. However, this model, what it allows you to do is to have weights that are not necessarily equal. So for example, in a 3-period moving average where we have weights involved, our weights can be W1, the first weight could be something like 0.5, and then W2 could be 0.3, and W3 could be 0.2. So we weight the most recent period 50%, the next one 30%, and the third one 20%. So that allows for sort of a non-equal weighting of each of the values in the weighted moving average. So that here is an example of applying the weighted moving average. Now I will demonstrate those for you just by using XLOM. We certainly could do the analysis in Excel. It will take a little bit of time, but we have some software that's available to us, which is an Excel add-in, and it's relatively easy to use that add-in. Okay, so we're just going to pause for a moment. So let's look at the next model, which is exponential smoothing. And exponential smoothing looks something like this. If we want to forecast for a given period, ft, what we do is we look at our error that we made in the last forecast, and we take a fraction of that error and adjust that forecast. So what happened is, this is what we're going to forecast for the current period, but this is our last period's forecast. Then we'll take this and adjust it by the difference between what the actual value was and that forecast that we made. So what is this piece right here? This is essentially an error that we made in period t minus 1. That's the error, and we're taking a fraction. So what happens is we will restrict alpha in such a way that alpha lies between 0 and 1. Another term that we use for alpha is called a damping factor, right? Or smoothing constant. Okay, now let's see why we would call it a damping factor. Let's see what happens. If we made alpha equal to 0, that's ultimate damping. What happens is this term goes completely out the window, and our forecast never changes. So the next period forecast is the same as the last period forecast. So essentially you get a really flat thing like this, a very fixed forecast. So whatever you start off with, that's what your forecast will be constantly over time. However, if we made it equal to 1, what happens is that this term will cancel out this term, and essentially what we would get is that ft would be at minus 1. That means our next forecast will be the actual from the last period. But what is this? This is the naive model. Alright? So if we now make alpha between 0 and 1, we're somewhere between doing nothing and then just being totally responsive. So that's why the value of alpha has a damping effect. When it's 0, total damping. When it's 1, no damping whatsoever. And so we got to find the right value of alpha that will come as close as possible to the actuals. Okay, what is that? We typically don't know ahead of time. We have to experiment a bit to figure out what that is. Now, in a case when we have trend, if we look at our data and our data looks something like this, you say, oh, there seems to be some kind of increasing trend if you look at that. And so with this increasing trend, if we were to use exponential smoothing model, we are reacting. Because we are reacting, we're not anticipating the trend ahead of time, and so we'll be lagging in our forecast. Well, this could be adjusted by a model called forecasting including trend. So if we want to do this forecast, it has two parts to it. This forecast including trend is made up of a smooth constant plus a trend component. And that smooth constant, ft, is really what we do is we take our last period's forecast and we do some sort of adjustment to it. So how do we do this? Well, here's what we do. It would look something like this. It would be fit t minus 1, right, plus alpha into a t minus 1 minus fit t minus 1. So we could write it out this way. You may see it in the text written this way, which it would be alpha times a t minus 1 plus 1 minus alpha fit t minus 1. It's exactly the same thing. This is just a rearranging of that formula. Okay. Now that's basically this part is the smooth component for the next period, and then we're going to do a trend component. And what do? With that trend component, what we will look at is we will take a fraction beta of the difference between our last two smooth components, this one and ft minus 1. In essence, that is some kind of projection of the trend. So we'll take a fraction of that, okay, and add to it, sorry, no, 1 minus beta times t minus 1, the trend component that we used in the last period. So when we combine those two things together, as you can see now, if we bring those two together, we now have our forecast including trend. All right, that model does a lot better than if we simply use the exponential smoothing model up here. All right, because as I mentioned, without doing any anticipation of the trend, we're lagging behind. So that's exponential smoothing using trend. What about trend models? Well, a trend, by definition, is some sort of constant upward or downward movement. In other words, it remains fairly consistent, or would you say constant but consistent upward or downward movement. So there's a trend right here if we look at this diagram. And most likely, if we talk about linear trend, then we can fit a following model like this. Y is equal to the intercept plus b1, and we would normally say x, but because we're talking about time series data, our independent variable x is really time. So we usually put t here instead of x. And we could fit that by doing, some regression analysis that you might recall from your earlier statistics course, where we find b1, which is the slope, by taking ss of xy over ssx. And you may recall the formulas for that look something like this. The sum of y over n, and then we divide it by sum of x squared minus the sum of x all squared over n. Something that looks like that. And then the intercept is calculated by taking the average of the y's minus the slope that we just calculated times the average of the x values. And then bring those two values together. Now, here where I said x is really t, the time. But if you look in textbooks, you will tend to see those formulas instead of t. And that could be done easily. Now, if you use Excel, Excel could fit a trend line rather easily. All you have to do is to give it the data, the two columns of the data, your x and your y's, and simply tell it fit a linear trend line or a linear line for that data for you. And then away you go. All right. So that's the case of the trend model. Now, if we're considering an associative model, and then we could talk about a linear associative model, sometimes we have the value that we want to predict is a function of several others. x1, x2, x3, xm, and so forth. All right. So if we're assuming that the function is linear, then we'll say y is equal to b0 plus b1x1 plus b2x2 plus bmxm. And that could be, for example, if we wanted to predict say sales in the summer, might be a function of things like population, temperature, right? And some other factors that we might be able to quantify. Whether or not there is some recreational activity that is going, you know, recreational activity. If we could quantify that, the number of major recreational activities taking place at a given point in time. So all these models are different types of models that we can use in helping us to do forecasting. So now I want to sort of demonstrate how we could do this forecasting in Excel OM for you without much difficulty whatsoever. Now, here's my Excel spreadsheet. You may recall that you downloaded Excel OM, which is an add-in. I'm using a Macintosh here. You would double click on the Excel add-in, and then you would see it would open Excel up automatically for you. And here in the Excel OM, we see many of the different tools that we could use in operations management, supply chain management, and so forth. In our case, we're interested in forecasting, so you could see we could do a simple moving average, right? Or we could do a weighted moving average. Now, you could always turn a weighted moving average into a simple moving average if you ensure that all the weights are exactly the same. And so why don't we just select an example here for weighted moving average. The number of periods of data, I will say that I have 6 periods of data. And then the number of periods in my moving average, let's just do 2 for now. And I'll just say weighted moving average. The sheet name, we'll call it 2MA, which basically means a 2-period moving average. And we could graph things as well. It's fairly straightforward. The template comes up looking something like this, and all we need to do is to put in the data. So I'm going to just widen the screen a little bit, make sure that you could see it. And if we did something else, let's see if we go 20, how does that look? And we double click, and away we go. I think we could see everything. So here's a problem. I'm just going to enter some data. 40, 50, 65, 75, 90, 110, something like that. And then for now, if I want to make this pretty much the same as a simple moving average, then I just need to make this 0.5 and 0.5. That's essentially a 2-period moving average. Alright, so as you can see here, 40 and 50 is 90 divided by 2. So here is my forecast 45. So I should be able to generate forecasts. So when I average 1 and 2, I get a forecast for period 3. So I should be able to generate 4 forecasts right here. And what do we have? 45 versus 65, 57. And as you can see, the forecasts are not very good. Part of the reason why they're not very good is because there's a trend line that is present that's not showing up here. So let's see. If you look at this, see? Here's the data. I have a trend, but because I'm using the last 2 periods to forecast the future, I cannot anticipate the trend well enough in this case. All right. So as you can see, very easily we're able to generate forecasts. If we go back to our data, then we actually have some values. We have the error. The errors come from the difference between the actuals. So for example, 65 minus 45 is 20. So these are our errors. These are our absolute errors. Okay. And if we square them, we get the squared errors. So we could generate a couple of different measures. One is called a bias, which is essentially just the sum of the errors to date. One is called a MAD. And so if you take the absolute values and you average them, so you can see the MAD and the bias are both the same. And then the mean squared error, which is if we take each value of the error and square them, for example, 20 squared is 400, and you add them all together and average that, you get the mean squared error. And my favorite measure is MAPE, the mean absolute percent error. So what would have happened in this case is I would have taken the error of 20 and divide that by 65, and that would be a percentage error based on just that actual right here. So 20 over 65. Then we take 17.5 over 75, which is basically a 23.33% error. Then if I took 20 over 90, it's a 22% error. And if I took 27.5 over 110, then I have a 25% error, right? So if I average all of those, what happens is that my average error is 25.33%. So I'm basically 25% off in all of my forecasts. And the reason why I like this measure is because I find the percentages a whole lot more tangible than using actual numbers, such as this case right here. But we do know in all of the cases, the larger the number, the worse our forecasting performance is. And so that's the case right here. That's exponential smoothing. Now, if we wanted to, not exponential smoothing, weighted moving average. If you wanted to do exponential smoothing, it's fairly straightforward. All we got to do is to go in here, or trend adjusted exponential smoothing. In this case, we would simply look at the number of past periods of data, which is 6. The title is Forecasting Including Trend. And we could call it a FIT, and we would need to then do a couple of things in this case. So I'm going to go back and steal the data from that first sheet right here, from our 2-period moving average. Here we go. I'll copy that. If I now go to fit and I put that here, we do this. Now, a couple of things that we need. We need the alpha value and the beta value. Alpha, let's just make alpha 0.5, and then we'll make the beta value 0.25, just randomly so. Okay, let's see if we did any better with our forecast. So we're somewhere still kind of below the actuals. So we probably should be a little more aggressive. Let's see if we could get a bit more aggressive. Let's go 0.8 and see what happens. And then maybe 0.5 on the trend and see if we did any better. Let's see. We came up a bit. So which means that what if we went 1 and 1 or 0.9, and I'm going to go about 0.75 here. Doesn't mean that beta has to be less than alpha, but I'm just testing it. We got a little bit closer still. So I'm sure that we could actually do something about this if we wanted to. Now let's see. If I have my tools here, solver. Do I have solver? Macro add-ins. Yes. Now I could attempt to see if I could find the best values of alpha and beta by using solver. First of all, let me just make the screen a little wider, and so that you can see what I'm doing. And so what I want to do is I'm going to try to, but look at my MAPE. Actually, the MAPE is not bad. It's actually 7.75% compared to 25% in the case of the moving average forecast. So we haven't really done badly at all. If I wanted to find the best values of alpha and beta, or the best value of alpha for a given beta, or the best value of beta for a given alpha, we could certainly do that. So what I'm going to do is I'm going to optimize this using Solver in Excel. So what does Solver do for us? It allows us to take a spreadsheet model and optimize an objective function. So here's what I'm going to do. With this, I want to minimize. I'm going to select here. I'm going to minimize the MAPE. Alright? And I'm going to select minimization. Well, what do I want to do? I want to minimize it by changing these two values right here. So that allows me to specify which cell values I want to change. But then I have some constraints. What are the constraints? I know that each of those constraint parameters, alpha and beta, must lie between 0 and 1. So I'll add a constraint that says this value is less than 1, and I will add that. I'll also take the same value and say that is greater than or equal to 0. I'll add that. Then I will take this value and say that is less than 1. I'll add that. And then I'll say the same value is greater than or equal to 0. And I will say OK because this is my last one. So here I got the constraints on these parameters. I have selected which cell that I want to optimize, and I want to minimize that. So I will tell Solver, go ahead and solve and give me something. So it's solving, it's found a solution. I say, okay, keep that solution, and look at this. I got it down to 7.41%, and both alpha and beta happens to be 1 for the optimal value. If we now take a look, it got a little bit closer, but we can't see a whole lot of difference between them. Alright? So using XLOM is fairly straightforward, and I don't need to demonstrate every single tool, but I think you could appreciate it that this kind of works. It's quite neat, and it works very easily. Let's do the last one. I'm just going to do a trend because there's clearly a trend present here. So I'm going to copy the data. I'm going to go back to XLOM, and I'm going to find a sheet that's empty. This sheet is not empty anymore. Oh, it is. And I'm going to select, this time, a trend. It's a trend production. So we have 6 values. Title, TRAND, trend, and in the sheet name I'll just call it TRND. Well, I could just put the E in there, no problem. And here we go. So our demand Y period, so you notice that the periods are just 1 to 6, but I'm going to put our demand right in here. So once I put that demand in here, away we go. Look at this. We need to change the graphing to a line graph. Let's see if we could quick chart. No, I want to change the gallery chart styles. I'm looking for a line graph if I could find it. Let's go. Should be able to change this. Here we go. Wow. Now look at this. Here's my trend line, and here is the original data. As you could see, there's not a lot of daylight between those two, which means that I should have a fairly good forecast in this case. Let's just look at the trend and see what we got. Wow. This looks quite cool. Just going to widen this a bit. And here we go. As you can see, look at our MAPE, 3.32%. So this is the best that we found so far. And so if you wanted to now project to the 7th period, we could do a forecast for the 7th period. And all we would have to do is to find the formula. And here's the formula right here. And do a projection. So in the 7th period, we're expecting the demand to be about 120, as you can see from over here. All right. So this is really cool. This was worked pretty easily. Like I said, we could do the manual computation via Excel, but with XLOM, our life is a whole lot easier. And so I hope you understand and appreciate how to use XLOM for forecasting. We could also use it for many other things, as you could see, decision analysis, location, plant location, center of gravity approach that we could specify, or we could do all these other aspects here, transportation, etc., etc., etc. Fairly straightforward. So that was sort of a quick summary of time series forecasting and the use of XLOM in actually solving some of the time series forecasting models.